Have you ever had one of those chats with an AI, maybe a customer service bot or like a virtual assistant, and you're just kind of amazed because it actually remembers what you said a minute ago?
Oh, definitely. Or when it pivots based on something subtle you asked earlier.
Exactly. It feels, well, almost like magic, doesn't it? Like it
hmm
gets the context. But behind that feeling, there's some seriously clever engineering going on, some really robust architecture. So today, yeah, we're doing a deep dive into LangGraph. It's this powerful framework, and it's really starting to change how complex conversational AI applications get built.
hmm
You can kind of think of it as, I don't know, the ultimate blueprint, like
Yeah,
a map for designing these AI conversations so they're not just, one step after another, but truly dynamic, intelligent.
right. And our mission today really is to unpack the core ideas of LangGraph. We want to show how it takes these potentially simple one-off interactions and turns them into these really rich, stateful dialogues, conversations that have memory. So we'll look at the basic building blocks, um, nodes, edges, that kind of thing, and then explore how they combine to create sophisticated decision-making, flexible flows, even things like running tasks at the same time or self-correction loops.
Wow. Okay.
Yeah, the goal is you'll walk away with a pretty good shortcut to being really well informed about the how, the mechanics behind truly smart conversational AI.
Fantastic. And to guide us, we've looked at several pretty advanced guides, some foundational documents, practical examples too. So we've got a pretty comprehensive look at the architecture and how it's used in the real world.
Sounds good.
All right, let's get started then. Okay, so let's really unpack this. When we say LangGraph, what is it, like at its most basic? And maybe more importantly, how is it really different from just, giving an AI a simple list of steps, like step one, do this, step two, do that?
Yeah, that's the perfect starting point. So at its heart, LangGraph lets you represent your whole AI application as what's called a directed graph.
Okay, directed
What's
graph
the
sounds a bit technical.
It does, but don't let that throw you. Just picture a really sophisticated flowchart, you know, a dynamic one.
Ah, okay, a flowchart. I can picture that.
Exactly. And in this flowchart, every distinct step or action your AI can take, that's a node. And the connections between these steps, the arrows showing the order things happen in, those are the edges.
Nodes and edges. Got it.
Right. Those two things, working together in the bigger picture, the graph, they define and run the whole agent's logic. So let's break those down a bit more. Nodes. Think of these as the individual, like, units of work. They're the doers, the thinkers, the
The
responders.
components doing stuff.
Precisely. And a node could be super specific, like
Yeah.
maybe just processing what the user typed in, pulling out
Yeah.
their name or the question they asked, like what's the weather, you know.
Mm-hmm.
Or another node might be all about calling an external tool, maybe hitting a flight booking API or getting stock prices.
Right, reaching out to the real world.
Exactly. And importantly, a node might just generate a response using a large language model, an LLM, turning maybe some complex data into just a normal sentence for the user. Each node is like a little piece of the puzzle doing its job, maybe updating the AI's memory and spitting out something the next step can use.
Yeah.
And then you've got the edges.
Mm.
So if nodes are the actions, edges are kind of the directions, or the connections, defining the
Yeah.
path, the order things execute in.
The arrows in the flowchart.
Yeah, but much smarter than just static arrows. They're really powerful because they allow for way more than just A, then B, then C. They enable that clever logic.
Ah, okay.
So you can have branching paths, right, where the conversation goes one way or another based on a decision. Or you can create loops, so the AI repeats something, maybe asking for clarification until it gets what it needs.
Like asking, sorry, could you repeat that over
Yeah.
and over?
Kind of, yeah. Or edges can even transform data as it passes from one node to the next.
Yeah.
They basically script the whole story the AI tells,
Mhm.
making it really adaptive instead of just rigid. And finally, the graph itself. That's the whole structure, the complete picture, connecting all these nodes and edges. It's the full blueprint, mapping out the entire journey from start to finish.
The whole map.
The whole map. It covers everything, the initial input, all the decisions, the tool uses, the final response. It's the big picture view of your AI's brain, really.
So, this structured flowchart approach, what does it really mean for us, the people interacting with these AIs or maybe thinking about building them? Why would a developer pick this potentially more complex flowchart way over something simpler? Is it just more complicated?
That's a really crucial question. And no, it's definitely not about adding complexity just because. It's about enabling capabilities that the simpler ways just, well, they can't really handle effectively. The main reason is building what we call stateful multi-actor applications. And that's where LangGraph really stands out compared to, say, the traditional chains you find in LangChain.
Stateful, multi-actor. What does that mean practically?
Stateful means it remembers things across the conversation. It maintains context. Multi-actor means it can coordinate different components, maybe different AI agents or even humans. A simple chain might be great for one task, like summarizing one article,
Right.
but it falls apart when you need the AI to remember what you talked about 5 minutes ago, or adapt based on that, or maybe hand off a task to a specialist agent and then get the result back. LangGraph gives you the structure to manage all that complexity.
You mentioned LangChain there. I've definitely heard of that, and I bet a lot of listeners have too. So how does LangGraph fit in? Is it like a replacement, or are they
Well,
different tools?
excellent question. It causes a bit of confusion sometimes, but no, they actually work together incredibly well. It's not really about replacing LangChain at all.
Ah, okay.
It's more about knowing their strengths and using the right tool for the job. And often, the most powerful approach is actually using them together. So when we talk about LangChain's chains, the simple ones, think of like an assembly line or a recipe.
Okay, fixed steps.
Exactly. A sequence of components linked up to process information in a fixed order. Load a document, split it, embed it, retrieve parts, feed it to an LLM for an answer. Step A, then B, then C. Always the same.
Right. Like summarizing an article, maybe?
Perfect example. Or extracting names from text. Things that are pretty linear, single-pass workflows. Chains are super efficient for that. LangGraph, though, with its graphs and state, it takes a much more dynamic, flexible approach. It represents things as these graphs. Think less assembly line, more like a dynamic decision tree that can loop back or jump around.
Like choose your own adventure.
Exactly like that. It excels when the workflow isn't just sequential. Maybe needs to loop back, ask for clarification, make decisions based on how the conversation is going, or even coordinate multiple actors, different AI agents working together.
And the state part.
Crucially, yeah, it actively manages the state of the conversation. It has this central memory, this persistent place to store everything relevant. That's how it maintains context over many turns. So why does this matter to, you interacting with an AI? Well, this is why it can feel like it remembers things. A simple LangChain sequence might answer your question and then completely forget it when you ask a follow-up.
Right, you have to start over. So annoying.
Exactly. But LangGraph's architecture, because it holds that state, it allows the AI to maintain context across lots of interactions. That leads to a much more coherent, personalized, and frankly, intelligent dialogue. It builds on what's been said.
That choose your own adventure versus a linear story makes perfect sense. It explains why some bots feel dumb and others feel, well, smarter. So if LangGraph remembers things, here's what I'm really curious about. How does it actually manage this memory, this context, across all those steps and decisions? What's the secret sauce?
You've nailed the absolute core concept there. It all comes down to something called graph state.
Graph state.
Yep. Think of it as the central shared memory bank for everything that needs to be kept track of across all the different nodes in your graph throughout the whole conversation.
AI scratchpad.
Exactly. Or it's short-term memory. It's constantly being updated, constantly being accessed. It's the hub for everything relevant, the current worldview of the AI for that specific chat. And you have to define it first. Graph state needs a clear schema. You basically say up front, okay, this is the kind of information I'm going to store here, and this is how it's structured.
So you plan the memory structure.
Precisely. And for complex stuff, user profiles, search results, things parsed from language developers often use tools like Pydantic models.
Pydantic? Why that?
Well, using Pydantic for graph state isn't just about structure. It enforces like type safety and data validation. It catches errors like trying to store text where a number should be before they mess up the AI's logic.
Ah, proactive error catching. Smart.
Yeah, it makes the AI's memory much more reliable, especially in complex systems. Then, as the graph runs, nodes perform state updates. Specific functions take the current graph state and whatever the node just produced, and they return the changes needed.
So a node does something, then updates the central memory.
Exactly. If a name input node gets the user's name, an update username function adds that name to the graph state. So the new info is immediately available for the next steps. And then critically, any node can access the current graph state. It can just pull out whatever information it needs.
Doesn't have to ask again.
Right. A search flights node just grabs the departure city, arrival city, dates right from the graph state. It doesn't need to prompt the user again for stuff it already knows. This shared memory access is what makes those coherent multi-turn conversations possible. The AI builds its understanding. And there's an advanced feature too, immutability. Sometimes you can configure it so previous versions of the state are saved.
Like version history. Why?
It's incredibly useful for debugging. You can literally trace back how the AI got to a certain point, or for auditing, or even potentially rolling back to a known good state if something goes wrong later. It's like a safety net.
Mhm.
So ultimately, this explicit management of graph state is why it matters so much. It's not just memory. It's giving the AI this persistent, evolving understanding of the user's context, their intent.
Moving beyond just Q&A.
Exactly. Think about that financial advisor bot again. It remembers your risk tolerance, your goals, your investment amount, all stored in graph state as it guides you. Each piece of info informs the next recommendation.
Without graph state.
Every interaction would be a blank slate.
Yeah.
You'd repeat yourself constantly. It'd be frustrating, ineffective. Graph state is the central nervous system that makes the AI feel truly intelligent over time.
Right. It's the AI's evolving worldview for that conversation, updated constantly. That totally explains the frustration with bots that forget everything. Okay, so graph state holds the knowledge, but what are the actual steps, the things that happen, and how do they make decisions or, get outside info?
Exactly. The graph state is the data center, but the work gets done by different types of nodes. They're the core bits that perform actions, make choices, change the state, and move the conversation along. So first, you've got agent nodes. People often call these the brains or the thinkers. They make the high-level decisions about flow or handle complex tasks, often using LLMs for reasoning.
Okay, the smart nodes.
Kinda, yeah. You can think of them by role, like a decision agent might look at a query and decide, human needed, or can the bot handle this?
So routing logic.
Yeah. For example, in customer support, an agent node gets, I can't log in. It uses an LLM to decide route to human, or suggest, try resetting your password.
Makes sense.
Then there are task agents. They do specific info gathering jobs. Maybe searching research papers, pulling info from a company database, or summarizing a long document that's already in the graph state.
Focused jobs.
Right. And state agents are specifically built just to manage and update the graph state itself, like guardians of the memory. These agent nodes give the AI its adaptability. Next up, tool nodes. If agents are brains, tools are the hands. They let the agent interact with the world outside of just text.
Like using APIs.
Exactly.
Yeah.
A tool node runs a function or API call and brings back the result. So maybe a search flights node queries a booking API, or a weather tool hits open weather map,
Why?
or even a custom science DB tool for a research assistant.
Giving the AI real-world powers.
Totally. Tools are critical. They let the AI get real-time info, do calculations, talk to other systems like CRMs or inventory databases. It gives the AI practical, actionable abilities. And finally, conditional nodes. These are the decision makers. They let the graph intelligently route the conversation based on criteria.
Like if-then statements.
Pretty much, yeah.
Yeah.
Based on the current graph state or what the last node did. For example, a chatbot handling weather, news, sports. A conditional node looks at the user query and routes it to the right handler node.
Directing traffic.
Exactly. Or think about online learning. After a quiz, a conditional node sends you to remedial stuff if you did badly, or advanced stuff if you aced it. Personalized instruction.
Nice.
Or an agent with a calculator tool. A conditional node checks. Did the user say calculate? If yes, route to the use calculator tool node. If no, route to the normal response node. These nodes create the branching logic that makes the AI feel adaptive.
Okay, so the nodes are the workhorses, the decision points. But how do we actually draw the lines between them? How do we create that flow, that dynamic conversation path?
That's where the different kinds of edges come in. They are literally the flow controllers, the navigators. They define how info and control move between nodes, dictating the path. They're the smart connectors. The simplest are sequential edges, just a direct straight line from one node to the next. Output of A goes straight into B.
Like our assembly line earlier.
Exactly. In an order system. Validate order, process payment, generate confirmation, send email. Each step follows the last fixed order. Perfect for predictable linear stuff. Then you have conditional edges. These are absolutely key for that dynamic routing. The flow depends on a condition checked against the graph state, or a node's output. Usually a function looks at the state and just returns the name of the next node to jump to.
So it chooses the next step based on what's happening.
Precisely. Think of that inquiry router node again. It uses conditional edges to connect to different agents.
Right.
Order tracking, returns processing based on the inquiry type it found in the user's message.
Right.
Or that sentiment analysis example. If sentiment is positive, a conditional edge sends it to the positive response node. If negative, it goes to the problem-solving node. That's dynamic adaptation based on context. And then there are function edges. These give you the most flexibility, the most power. You define a custom Python function that can either transform the data flowing between nodes.
Change the data format.
Yeah, exactly. Like if one node outputs a dictionary username, Alice, product, laptop, a function edge could turn that into a nice sentence. The user Alice is interested in a laptop before sending it to the next node.
Smoothing the data flow.
Right. Or the function edge can use custom logic to dynamically decide the next node. Imagine an intent classification node. A function edge could take the intent, product inquiry, order status, and use a function to route to the specific node built for that intent. It allows really complex routing based on nuanced understanding. Function edges let you embed custom logic right into the connections.
Okay, wow. Nodes act and decide, edges direct the flow and transform data, and graph state holds the memory. It sounds incredibly powerful, very flexible. But for someone just starting or building something simple, how does it all actually fit together? Can you give us a really basic, practical example?
Absolutely. It's vital to see it in action, even simply. Let's use that classic super simple example, the simple greeting chatbot. Seems trivial, but it shows the core idea beautifully.
Okay, a greeter bot.
Yeah, so you define a few nodes, maybe a greeting node that just says, hello, welcome, then a name input node that asks, what's your name? And finally, a confirmation node that says something like, hello, user's name, how can I help? 3 simple steps.
Got it. Greet, ask name, confirm name.
Exactly. Then you connect them with edges. Mostly simple sequential edges here. Greeting node, name input node, then name input node dash confirmation node. Just a straight path.
Linear flow.
Right. But here's the key. The graph state. You'd set it up to store the user's name. So after the name input node gets the name, it updates the graph state, adds the name in there.
Puts the name in memory.
Exactly. Then, when the confirmation node runs, it doesn't just say hello. It accesses the graph state, pulls out the stored name, and uses it in the response.
Ah, so that's how it remembers the name.
That's the magic. The chatbot remembers because the name is persistently stored in graph state and then retrieved later. Even this super basic example shows how LangGraph builds context and memory. It's not just isolated steps. Past info influences future responses. That's the shift to dynamic state-aware dialogue.
That's brilliant. It makes the memory part really clear, even in that simple case. So, okay, for linear flows, branching paths, incredibly powerful. But what about needing the AI to repeat something, like getting feedback again and again to make a recommendation better, or breaking a big problem down into smaller, similar bits? Can the graph do that, or is that a different technique?
No, that's an excellent question, and it's exactly where LangGraph moves beyond just simple decision trees and really uses its graph powers. It absolutely supports loops and recursion, essential for that kind of iterative refinement or breaking down complex tasks.
Loops and recursion in a graph. How does that work?
Well, the core concept is pretty neat. Loops mean repeating a set of nodes until some condition says stop. Think of a feedback cycle. Recursion is when a node or a sequence essentially calls itself to solve a smaller version of the same problem, like breaking a big task into mini tasks.
Okay.
And both are implemented using conditional edges that just loop back to an earlier node in the graph.
Yeah.
Creates a cycle.
Ah, an edge pointing backwards.
Pretty much. Let's take an example of loops. Think about recommending products on an e-commerce site, but interactively.
Okay.
The graph could start with some broad recommendations. Then it enters a loop. Step 1, show recommendations, get user feedback, thumbs up, down, maybe. Step 2, update the recommendation logic or user profile and graph state based on that feedback. Step 3, generate new, hopefully better recommendations. Step 4, loop back to step 1 to show them and get more feedback.
Until the user is happy.
Exactly. Or until you hit a limit, like maybe 5 rounds of feedback. It's way more dynamic than just one-shot recommendations. It learns in the interaction. And for recursion, imagine a really complex problem-solving task. A node acts as a task decomposer. It asks, is this task simple enough to solve right now?
Base case, like in programming.
Precisely. If yes, solve it. If no, it delegates the task to another instance of itself, or a specific subgraph, but with a simplified version of the problem. It keeps breaking the problem down recursively until it hits those simple base cases it can solve. Then the results get passed back up the chain.
Like how humans tackle huge problems, break them down.
Exactly. It's how an AI could handle complex research queries or maybe even writing intricate code by recursively simplifying. But, and this is crucial, for both loops and recursion, you must have a clear termination condition.
A way to stop.
Absolutely. Otherwise, you get infinite loops, infinite recursion. The AI runs forever, eats resources, crashes. That condition tells the graph when to stop repeating or breaking down and move on, essential for making it actually work.
Right, you need an exit strategy for the loop or the recursion. That makes sense. It sounds powerful, but maybe a bit tricky to debug if something goes wrong in that loop. How do you trace that?
That's a really sharp question. The dynamic nature can make debugging seem harder, but actually, LangGraph's structure helps a lot here.
Oh, how so?
Because everything relies on that explicit graph state and defined nodes. You can easily add logging to see the state before and after every single node runs. It creates this incredibly detailed audit trail.
So you can see exactly how the memory changed at each step.
Exactly. And remember that immutability thing. If you save previous states, you can literally replay the conversation step by step, including through loops, to see where things went sideways or why a loop finished or didn't. That transparency is a massive advantage compared to systems where the state is all implicit and hidden.
Ah, okay, so the explicit state actually makes debugging easier in some ways. Cool. Now, shifting slightly, loops are great for repetition. But what if the AI needs to do several different things at the same time to be faster? Like checking flight prices, A&D hotel availability simultaneously, not one after the other. Can the graph handle that parallelism?
Absolutely. And that's another major strength, parallel execution. It's all about boosting performance by running independent tasks concurrently. Game changer for responsiveness.
Doing things at once, how's that work?
The concept is simple. LangGraph lets you run multiple nodes at the same time instead of strictly one after another. It's perfect when those nodes are doing things that don't immediately depend on each other's results.
Like checking flights and hotels, they're separate searches initially.
Perfect example. Or fetching a user's account balance from one system and their recent orders from another. They're independent, so run them together. Saves the user waiting time. And the benefits are huge. The big one is cutting down processing time. If two tasks take 5 seconds each, running them in parallel takes roughly 5 seconds total, not 10.
Half the time.
Potentially, yeah. Leads to better throughput handling more users and much faster response times for the user. That's critical for making the AI feel fast and smart. Plus, it uses your computer hardware more efficiently. It's often the difference between an AI feeling sluggish versus instantly pulling together complex info.
Makes total sense. Can you give another example?
Sure. Back to that travel agent. Instead of search flights, wait, search hotels, LangGraph. LangGraph can trigger both searches in parallel.
Ah,
Both API calls run at the same time. Once both results are back, then they feed into maybe a present options node that combines everything for the user, or that customer service bot. Fetch balance and order history concurrently, then show both. Much quicker for complex queries. There are some considerations, though. Usually when nodes run in parallel, they each get the same starting state from before the parallel block began.
meaning changes in one parallel node aren't seen by the others while they're running.
Generally, yes, not during that concurrent execution itself. If they needed to share info mid-run, you'd need something extra, maybe like a shared cache they both write to and read from. But often, the point is independent execution, so needing to sync after they finish is usually fine and simpler.
Okay, so parallelism for speed on independent tasks. Got it. So we've got loops for repetition, parallelism for speed. This is getting sophisticated. But what about just sheer complexity? Imagine building that whole returns process for a customer service bot. Dozens of steps, decisions. Wouldn't the main graph just become a giant, unreadable spaghetti monster of nodes and edges? How do you manage that?
You've hit the nail on the head, and the answer is subgraphs. That's exactly how you tame complexity in big AI applications and keep things organized.
Subgraphs, like smaller graphs inside the main one.
Exactly. Think of it like a function or a module in regular programming. It's a self-contained bundle of nodes and edges that performs one specific well-defined task.
Okay, encapsulate complexity.
Precisely. You could design a whole mini-graph just for handling returns. Ask for order number, reason, check policy, confirm, initiate refund, send confirmation. All those steps.
Right, a whole self-contained process.
Yeah. And once you've built and tested that return subgraph, you could just plug it into your main graph as a single handle returns node.
Ah, so the main graph stays clean. It just sees handle returns, not all the messy details inside.
Exactly. It hides the complexity. It's like collapsing a detailed diagram into one box labeled returns process. And the benefits are massive for building real systems. First, modularity breaks complex systems into smaller, understandable chunks. Easier to grasp, easier to debug.
Makes sense.
Second, reusability. Build the subgraph for, say, user authentication once, then reuse that same subgraph anywhere you need login in this app or even others. Saves huge amounts of time, ensures consistency.
Build once, use many time.
Right. Third, maintainability. Need to update the returns logic. You just edit the return subgraph. The main graph doesn't need to change, reducing the risk of breaking unrelated things.
Isolate changes. Good.
And fourth, testability. You can test each subgraph on its own, make sure it works perfectly before plugging it into the bigger system. Simplifies testing hugely. So for that customer service bot example, the main customer service graph handles the top-level flow. One node in it, handle returns, is actually that whole complex returns subgraph. Another node may be human escalation, could be another subgraph handling the notifying an agent, passing the history, getting the agent's reply back. Makes integrating humans really clean, too. It's how you build really complex stuff without losing your mind.
That's fantastic. Subgraphs for organization and reuse. It really sounds like bringing good software engineering principles into AI conversation design. Okay, so we've got this brilliant, stateful, adaptable AI design with LangGraph. How do we make it work in the real world? How does it, play nice with other AI tools people are already using and handle actual production traffic?
Crucial questions. It's all about leveraging the ecosystem and focusing on operational excellence. LangGraph isn't an island. Its real power comes when integrated and deployed properly. It's the difference between a cool demo and a reliable service. First, let's talk integration with LangChain, the power duo. We touched on this, but it's key. LangChain has this incredibly rich toolkit for building agents that do things, interact with APIs, databases, generate code. LangGraph provides the framework to orchestrate those agents in complex workflows.
So LangChain does the tasks. LangGraph manages the overall process.
That's a great way to put it. LangChain agents are great at doing. LangGraph is great at managing the doing, deciding what gets done when, coordinating multiple doers, keeping track of the big picture state. They're much stronger together. And there are a couple of main methods of combination. One is using LangChain agents as tools within your LangGraph, like specialist contractors managed by LangGraph, the project manager. So your LangGraph might manage a research project. One node calls a LangChain agent specialized in literature reviews. Another node calls a different LangChain agent for writing code based on the review. A third calls another for deployment. LangGraph handles the overall strategy and state, leveraging LangChain's specific skills. The other way is to build custom agent logic inside LangGraph nodes. You can embed agent-like behavior directly in a node using LangChain components, LLMs, prompts, smaller chains within that node's logic.
Tighter integration.
Yeah. Maybe a LangGraph node needs to summarize the conversation so far. It could directly use a LangChain LLM chain with a specific prompt right inside its own code. Gives you fine-grained control over how LangChain bits contribute to the LangGraph flow.
So it's really about composing them, using the best parts of both. Makes sense. But okay, the application is built. Now, production. Thousands, maybe millions of users. How do these LangGraph apps scale? How do they handle that load without just falling over?
Scalability. Yeah, absolutely critical. A production LangGraph needs to handle fluctuating traffic, high demand, dynamically grow and shrink. And why it matters is obvious. If your AI gets popular, one server won't cope. You need a system that grows with demand, stays performant, stays available. No crashing, no slowdowns.
So how do you do that? More powerful servers.
Sometimes. But the standard approach relies on containerization with Docker and orchestration with Kubernetes.
Docker and Kubernetes. Heard of those?
Right. Docker packages your app and everything it needs into a neat container. Runs the same everywhere. Kubernetes then manages deploying, scaling, and running those containers across a whole cluster of machines. It automates the hard parts of running stuff at scale.
Yeah.
And the core concept for scaling AI like this is horizontal scaling. Instead of making one server bigger, vertical scaling, which hits limits, you spread the work across many identical instances of your LangGraph app.
Run multiple copies.
Exactly. And a load balancer sits in front like a traffic cop, sending incoming requests to the least busy copy. If traffic surges, Kubernetes automatically starts more copies, the load balancer includes them, and you scale out seamlessly. But, crucially for LangGraph, you need distributed state management. Since LangGraph needs that graph state for each conversation, and you have multiple copies of the app running.
They all need to see the same memory for a given conversation.
Precisely. You can't store the state just in the local memory of one copy. You need an external shared place for it, usually a fast database or cache like Redis or maybe Cassandra.
So the state lives outside the application instances.
Yes. Any instance gets a request, fetches the conversation state from the shared store, does its work, and then updates the state back in the shared store. That way the conversation stays coherent, no matter which instance handles the next turn. Seamless continuity for the user.
Wow, okay. The AI's memory isn't just in one brain, but shared across a whole network of them. That's a major architectural consideration. Okay, so it's designed, deployed, scaling. But the real world throws curveballs. APIs fail, users type weird things. What happens when things go wrong? How do you make LangGraph robust, stop it from just crashing?
Robustness, yeah.
Yeah.
Absolutely critical. Building production AI means expecting errors and handling them gracefully. Otherwise, crashes, weird behavior, frustrated users. Reliability is king. So some key techniques LangGraph helps with. First, retries for transient failures. Things like temporary network glitches calling an external API.
Little hiccups.
Right. You design nodes to automatically retry a few times, maybe wait a bit between tries before actually giving up. Wrap the API call in a retry logic. Stops minor issues, killing the whole conversation. Second, error propagation. If an error can't be fixed by retrying, the graph needs a plan. Don't just crash. Route the execution to a dedicated error handling node.
A specific node just for errors.
Yeah. It logs the detailed error for developers, maybe sends an alert, and crucially gives the user a helpful message. Sorry, something went wrong, please try again later, or I've notified a human to help. Graceful failure, not a confusing crash, and a more advanced but super powerful technique. Checkpoints and rollbacks.
Yeah.
Think of it like saving the game.
Save points in the conversation.
Exactly. Save the graph state at known good points. If something goes wrong later, maybe an LLM gives a bad response or a tool fails non-transiently, you can roll back the graph to the last good checkpoint.
Undo the bad step.
That's precisely. Undoes the problematic changes, lets the system maybe try a different path or prompt the user differently from that save point. In that travel booking example, if the flight search fails badly, roll back to before the search, let the user change their dates or budget, and try again. Much better than starting the whole thing over. Incredible resilience for complex flows.
Wow. Save games for AI conversations. That's a fantastic way to think about resilience. Okay, final area. With all this power comes responsibility. Ethics. How does LangGraph, as a framework, help ensure these complex AI systems are fair, trustworthy, responsible?
That's a vital question. LangGraph itself isn't inherently ethical, it's a tool. But its structured explicit nature provides really strong architectural hooks to implement responsible AI principles. It gives you the control points.
How so?
Well, that explicit structure supports input validation really well. You can have nodes specifically designed to check user inputs, filter out malicious instructions, prevent prompt injection, block inappropriate content before it even hits the LLM, a key safety layer.
Okay, filtering bad input.
Yeah. And prompt engineering, which is crucial for controlling LLMs, can be managed within dedicated nodes. You can standardize prompts, building guardrails against bias or harmful outputs, make them easier to audit. For data minimization, defining that graph state schema explicitly encourages you to only collect and store what's truly necessary for the conversation. Helps avoid grabbing too much personal data. Aligns with privacy rules like GDPR or CCPA.
Building privacy in.
Right. And security benefits too. Structured state makes it easier to encrypt sensitive data within graph state, at rest, in transit, and implement fine-grained access controls which nodes can see or change which parts of the state. And finally, monitoring and logging. LangGraph's ClearFlow makes it easy to add detailed logging to nodes and edges. You can track exactly what the AI did and why. This is invaluable for detecting weird behavior, identifying potential biases in real-world use, and auditing interactions for compliance. Transparency builds trust.
So it's not a magic ethics button, but LangGraph's structure gives developers the tools and visibility they need to build more responsible, auditable, and controllable AI systems.
That makes a lot of sense. Okay, so wrapping this up, what does this all mean? We've really dug into LangGraph's power. Its graph structure, that crucial graph state for memory, handling loops, parallelism, subgraphs for complexity, integrating with tools like LangChain, and thinking about real-world deployment and responsibility. It's a seriously robust blueprint for intelligent, adaptive AI. It feels like the key to moving away from those frustrating, rigid bots towards interactions that feel genuinely smart, context-aware, and actually helpful.
Absolutely. And if we zoom out, connect this to the really big picture. Imagine AI not just answering questions based on its programming, but actively learning and adapting its own internal pathways from every single interaction.
Learning how to have better conversations.
More than that, dynamically reshaping its own decision-making logic, almost like our brains do when we learn or solve new problems, not just memorizing, but fundamentally changing how it thinks and responds. Wow.
So the provocative thought is, how might LangGraph's dynamic stateful architecture be a stepping stone towards truly self-improving AI? AI that can adapt, innovate its own processes in real time, maybe even learn to fix its own biases or refine how it uses tools, all without needing constant human hand-holding and retraining.
That is definitely a profound thought to chew on, an AI that learns and reconfigures itself. Fascinating, maybe a little scary too. Understanding these foundational tools like LangGraph really does seem key to grasping where AI is headed. We hope this deep dive gave you a valuable shortcut, made things clearer, and maybe sparked some new questions for you too.